This is book 1 of 2. It's going to cover motors and motor control. The first part of this session is going to be e-stop circuits and switching relays. And then the second portion is we're going over how we wire our safety into it, and then actually lots of the devices and how they're wired past the safety part. A circuit breaker is a type of switch that automatically stops the flow of electricity. It trips in an electric circuit to protect the circuit. The main use of a circuit breaker is to protect against overload or a short circuit, which usually will ruin devices. Circuit breakers must be manually switched back on after they have been tripped, which means that they can be reused. Here's what a circuit breaker looks like. Next, let's talk about fuses. Fuses, when they stop the electric current, they literally blow and they cannot be reused. The main use of a fuse is to protect against overload or a short circuit. Both these situations can cause major damage due to an overload of current. Fuses must be replaced after they have been blown. This means that they cannot be reused after it's broken the circuit. Fuses come in many different shapes and sizes. Most common fuses will blow instantly and it will stop the current. Some fuses have a certain time period where it allows a higher amount of current over the rating to pass through, and these are called slow blow fuses. Just like a circuit breaker, the line power comes in from the top and exits through the bottom, called the load power, which supplies power to the devices. Alright, now let's talk about push buttons. A push button is a type of switch that starts or stops the flow of electricity in an electric circuit. The main use of a push button is to give control of an electric circuit to an operator. There are many types of push buttons. At WPA we have 2 types, a push-pull and a momentary. Momentary push buttons will only stay closed as long as they are being pressed. A push-pull button will hold their position, open or closed, until manually pushed, closed, or open. Most of the push buttons at WPA are e-stops. The e-stops illuminate red when pushed in. In the pushed position, the connections are B1 to B2. In the pulled position, the connections are A1 to A2. Here's how we typically wire an e-stop push button. The X1 terminal, you wire up the lamp AC voltage. The X2 terminal, you wire up the lamp common. The A1 terminal is the normally closed common. The A2 terminal is the normally closed load. The B1 terminal is a normally open common, and the B2 terminal is a normally open load. Here's how we wire the WPA e-stops. Here's some top and bottom views of the Allen Bradley e-stop we use at the plant. In the top view, in terminal A2, the pink wire is going to the PLC. It's the e-stop when it's not pushed. It gives the PLC the signal that the e-stop isn't pushed. In the top view, you can see that the A1 and B1 terminal are jumpered with 120 volts. As well in the top view, in terminal A2, a pink wire is going to the PLC when the e-stop is not being pushed. On the top view, in terminal B2, it connects to the bottom view, terminal X1, to give AC voltage for the push button light. On the bottom view, terminal X2 is your common or neutral. An example of an output device in the plant is a stack light, and here's how to wire it. In terminal 5, it supplies AC voltage to light number 5. In terminal 4, it supplies AC voltage to light number 4. In terminal 3, it supplies AC voltage to light number 3. In terminal 2, it supplies AC voltage to light number 2. And in terminal 1, it supplies AC voltage to light number 1. And then terminal 0 goes back to your neutral. It's good to know that a stack light is a good example of an output device. What differs between an input and an output signal is the input, or an e-stop, gives information to the PLC. The stack light takes information from the PLC and outputs light. Let's move on to relays. Relays are a type of switch. A switch can be in one of 2 states: closed, allowing electrons to flow, and open, stopping electron flow. A relay allows one switch, called the coil, to control multiple circuits. A relay is activated when the rated voltage flows through the coil. Essentially, the coil powers the relay. Relay contacts can either be normally open, NO, or normally closed, NC. Normally open contacts will only be connected when the relay's coil is activated. They are sometimes called a make contact. Normally closed contacts will only be connected when the relay's coil is not activated. These are often called break contacts. Relays can be classified by poles and throws. The number of poles in a relay indicates the number of circuits controlled by the relay's coil. Single pole, SP, means the relay coil will only control one circuit. Double pole, DP, means the relay's coil will control two circuits. If a relay has only a normally open contact or only a normally closed contact, these are called single throw, ST, relays. If it has both types of contacts, it is called a double throw, DT, relay. At WPA, we use mainly three different types of relays. All three of them are DP-DT, double pole, double throw. All right, let's take a look at how we wire these relays. Terminal A1 supplies AC power to the coil. Terminal A2 supplies the neutral wire. Terminal 11 is circuit 1 common. Terminal 12 is circuit 1's normally closed. Terminal 14 is circuit 1's normally open. Terminal 21 is circuit 2's common. Terminal 22 is circuit 2's normally closed. Terminal 24 is circuit 2's normally open. When the relay is activated, terminals 11 is connected to 14 and 21 to 24. When the relay is not activated, terminals 11 is connected to 12 and 21 is connected to 22. Now let's look at how we wire a relay. Terminal 21 is circuit 2's common. Terminal 22 is circuit 2's normally closed. Terminal 24 is circuit 2's normally open. Terminal 11 is circuit 1's common. Terminal 12 is circuit 1's normally closed. Terminal 14 is circuit 1's normally open. And terminal X1 is the coil's AC power going in. Terminal X2 is the coil's neutral. Let's move on to another type of switch, contactors. A contactor is a switch that operates just like a relay. A contactor is used in place of a relay because it can pass a lot more current. A contactor is being controlled by a circuit that requires lower power than the circuit that is doing the switching. Here's how we wire up a contactor. The A1 terminal is supplied AC power for the coil voltage. The A2 terminal is the neutral wire. Terminal 1 is the circuit 1's common. Terminal 2 is the circuit 1's normally open. Terminal 3 is circuit 2's common. Terminal 4 is circuit 2's normally open. Terminal 5 is circuit 3's common. Terminal 6 is circuit 3's normally open. Terminal 13 is circuit 4's common. And terminal 14 is circuit 4's normally open. When the relay is activated, terminals 1 is connected to terminal 2, terminal 3 to terminal 4, terminal 5 to terminal 6, and terminal 13 to terminal 14. When the relay is not activated, no connections are being made. These Allen-Bradley contactors are commonly found in the plant. Here's how we wire up a contactor. Terminal A2 supplies the coil's neutral. Terminal 1 is circuit 1's common. Terminal 2 is circuit 1's normally open. Terminal 3 is circuit 2's common. Terminal 4 is circuit 2's normally open. Terminal 5 is circuit 3's common. Terminal 6 is circuit 3's normally open. Terminal 44 is circuit 4's common. Terminal 43 is circuit 4's normally open. Let's talk about the control power circuit. Control power is usually a signal that signifies all safety and other hardwired permissives were checked and passed. The main use of control power at WPA is to allow a safety circuit to break all motor power instantly and without the PLC logic should an issue arise. In some instances, certain instrumentation may be deemed important enough to allow it to be on the control power circuit. One example of this is the silo pressure switches. If a silo pressure switch trips, it cuts the control power for the silo motors instantly without PLC logic. Let's walk through the basic WPA control power circuit. If all the E-stops have power, and all the E-stops push buttons are pulled out, and any other permissive is okay, such as the silo pressure switch, then it energizes the contactor, which then allows control power to enable the field devices. There are multiple ways to wire up a control power circuit. Typically, when an E-stop button is pushed, an operator would have to go around to each E-stop and find visually which one was pushed in. Here at WPA, we have a better approach. We wire each E-stop into a DP-DT relay. The relay is then wired in series with the next E-stop's relay. If any E-stop is pushed, it kills power for every relay after it, which breaks the current to the contactor, which stops the motor. The second pole supplies a signal to the PLC, telling it whether the E-stop is pushed in or not. So in the end, an E-stop will kill all power to every device after it. So we've talked about E-stop switches, we've talked about relays, and we've talked about contactors. And we've talked about all the poles and switches that are within them. So knowledge about our motors and motor control and how our E-stop control power circuits are wired allows us to do our jobs more safely and efficiently every day. Thank you for watching.